Welcome back to ECE 320A. We are in Unit 9, which is our transfer function unit, and we're trying to gain better understanding of how a system's transfer function helps us determine what will be the output response of a system when we apply particular input waveforms. And in this particular video, what I want to do is talk about how we can use MATLAB to actually provide us with a way to develop an intuitive understanding through the graphical figures that MATLAB is able to generate so that we can start to see what happens if we hit a system with an impulse, if we shake a system at a particular frequency, if we excite a system with an exponential waveform, what's going to result at the output? We already know how to solve that. We can go into the frequency domain, multiply the transfer function times the Laplace transform of the input waveform signal, and that will produce the Laplace transform of the output signal. We can inverse Laplace transform that output signal's Laplace transform and obtain the time domain response, which is what we will see at the output from that particular system's transfer function. We're trying to look at two in this video. One is to examine an exponential waveform, and that is now just simply something that looks like that. And the second waveform that we will inject into our system using MATLAB is a sinusoidal waveform. We're going to excite our system with a sinusoid, and we want to see what actually comes out at the output. We're going to see, and I can't emphasize this enough, that when you shake a system, that's what I'm meaning here when I say something like this. This is now, we are shaking the system with a sinusoid. We just keep shaking and shaking and shaking. We don't change anything. We just always shake at a particular frequency. What's going to happen in a linear system is the output is going to, after the transients have disappeared, so now we're talking about under steady state conditions, after the transients have finished, which is after 5 time constants, then the output signal will actually be shaking at the same frequency or oscillating or vibrating at the same frequency that we are exciting the system with. It may have a different amplitude, obviously, because the system changes things, and it may delay the time between when we have peaks in the input and when we see peaks in the output. And that's what we want to start to understand and get a feel for in this video. Let's do this with a very classic system. We'll continue to work with a low-pass filter. Hopefully you can tell me even more about this low-pass filter, and you'll even be telling me more once we get into Unit 10, which we're talking about frequency response and Bode plots. This is a first-order filter. It has a s plus 10 denominator factor. It has a pole at s equal to minus 10, the value of s that causes the denominator to vanish. It has a DC gain of 1, which we can find the DC gain when we replace s with a frequency of 0, s equal to 0, and we get 10 over 10, or a gain of 1. So if we put in a DC signal, a constant input signal, we should see at the output the same amplitude waveform coming out, and it would be constant. Here is our frequency domain block diagram depiction of what we're doing. We're exciting our low-pass filter, a system, with an input, capital X of S in the frequency domain, and finding or producing an output, capital Y of S. Here's what's happening in the time domain. If we excite the system with an exponential waveform, it now gets processed through the system that has an impulse response, h sub 1 of t, and that will produce now an output response, y of t. And in the time domain, we're actually convolving these time domain signals to produce the output. And what's the output going to do? Well, if the impulse response was a pure impulse function, and we know what that is, that's this infinitely tall peak with an area underneath that peak of 1. If h sub 1 of t was an ideal impulse function, then y of t would look exactly like x sub 1. In this case, our low-pass filter doesn't quite look like an ideal impulse function, and for that reason, y sub 1 of t is not going to look quite like x sub 1, but it may start to look like x1 after a little bit of a transient. So we might expect something like y sub 1 of t that I've shown here. What's going to happen when we apply a sinusoidal signal to the same low-pass filter? Again, in the time domain, we convolve h sub 1 of t with x sub 2 of t, and we would expect then that in the output, maybe after a transient, and I'm exaggerating that transient behavior, we will start to see a signal that is of the same frequency, and the frequency we can simply measure by looking at two common points on the waveform. There is our period, and we know the period is related to the frequency of oscillation either in hertz or in radians per second. We know that omega is 2 pi f, and f is 1 over t, meaning if we measure t, then we know the frequency in hertz by its reciprocal, or we know its frequency in radians per second by looking at 2 pi over t. And we will see then that this waveform has the same period in the steady state interval, and right here is where I'm saying we have our transient behavior. Now I'm exaggerating that transient shape, but just to make a point. And this transient is 5 tau, so we would look at the exponents in our system's impulse response and see what's the slowest, what's the dominant one, and that we would then approximate as our tau of the overall system, and we would say, okay, after 5 of those, we've reached steady state. Today we're going to, in this video, look at a MATLAB way of producing what I've tried to sketch or animate here in the time domain. All of this below the dashed line is our time domain behavior. And you really should be sort of seeing this or envisioning this even when you were seeing this block diagram description. Hopefully you are starting to become comfortable with going from the transfer function of our system to its impulse response. In this case, it's a first order, so that shouldn't be that much of a stretch. But in MATLAB, what we want to do is we want to show how straightforward it is. So if you open up MATLAB, you will see many different windows, but we will now be operating in this command window and typing commands on the command line, which are now these two arrows that we are typing on. We have our second window that's sort of above the command window that's showing us the editor, where we would then type in a string of commands if we wanted to start writing up a program. And in this case, I've already introduced VID for video 9.4, and what we want to do is actually execute that, and you can see that the current folder, which is telling us it's in the C drive at a very specific location. I've gone ahead and introduced a specific folder for this class, and that folder is 320A Fall 17, and that now gives us this current folder's contents, which right now I only have one script file .m in that. And this workspace will keep track of the variables that are introduced as we type in commands. I'm going to actually execute the commands in this script file, which are actually illustrated or shown here in this editor window, and I will provide that information to you also in OneNote or with a set of notes, but we will then execute these sets of commands. And what we want to do first is create the transfer function, and that's fairly straightforward in MATLAB. We simply issue the function TF and have particular arguments. We have a numerator argument, that's the first argument, and then we have a denominator argument, and any polynomial is now written as a row vector. So in this case, we now start at the rightmost element in that row vector, and we say we have 10 plus, these are all coefficients, then we start going to higher powers of s. Then we have 1 times s, and that's as high as we go. In the numerator, all we have is a constant, which is 10. So that's how we now can express a polynomial as a vector in MATLAB. We simply look at the coefficients of the s terms and place those in the appropriate location of this row vector. Another MATLAB command or function impulse on the defined transfer function capital H1 allows us to quickly see what the impulse response of that transfer function looks like. Then we will create an exponential waveform, which we said is what we're doing here with x of 1 of t. So we should expect to see something like that, and it now has this exponential decay impacted by the exponent minus 2t, and we're only turning that on at time 0 or for non-negative values of time. Then another command within MATLAB allows us to essentially convolve h sub 1 of t and x sub 1 of t, or we can use, actually in this case, we're using the transfer function, capital H1, and doing a linear simulation, that's the LSIM, with the appropriate arguments. We need to put in the transfer function, which is right here. Then we put in the input waveform, and we have a vector that's our time vector. And with those particular inputs, and if you don't want all of this data to be displayed, you might follow that with a semicolon. Then that will produce a y sub 1 of t, which we hope looks maybe something like we're anticipating we've sketched here for y sub 1 of t. Then we want to shake the system with a sinusoid. In this case, it's a cosine waveform with a frequency omega of almost 30 radians per second. We have a frequency of 5 hertz. So 2 pi, here I'm approximating pi to be 3. Maybe that's a gross approximation, but that's close enough for what we need to do today. And we can now do the same thing. We can use the LSIM command to generate y sub 2, and what we will see is after the transients, or in the sinusoidal steady state, that's what the SS subscript stands for, we will see that the input that we started with, which had a magnitude of 1, now its magnitude is influenced by the magnitude of our system's transfer function evaluated on the imaginary axis. Now we're using S here. Equal to j omega, and the omega is 2 pi 5, which is the omega that we have as the argument of our input waveform. That magnitude of our transfer function at that frequency changes the magnitude of our input waveform x sub 2 of t, and it also introduces a phase shift associated with the angle of that complex number that will result when we evaluate our transfer function. Again, we're going back to the transfer function and replacing s with approximately J30. And then we need to find, so now we have 10 over J30 plus 10. We want to find what is that complex number in terms of a magnitude and an angle. That's in polar form, and that provides us then with the magnitude change of our input and the phase change in our sinusoidal input signal that produces the sinusoidal steady state output. Just for fun, we'll check this. We'll look at the Bode plot of H1. Again, when you're working in chapter 10, you might want to be able to quickly know what's the answer in the back of the book. Well, now you'll be able to introduce or use MATLAB as a way of checking your work. You can find the transfer function or create the transfer function and simply issue the function Bode in MATLAB, and that will produce the the Bode plot for that particular transfer function. We can also use a couple of other functions in MATLAB. Absolute, which is taking the absolute value of a complex number, which this will be in general a complex number, and we can find the angle, and that angle may be expressed in radians, so you need to make sure that if you're thinking degrees, that you convert from radians to degrees. So let's go ahead and issue those commands. If we go back to MATLAB, I've already typed in the command window and on the command line VID 9.4, and that's a script file in the current directory, so that should execute. And maybe I should have done this before now, but now there's the transfer function. I found the poles and zeros of that particular transfer function. We had a pole at -10. We have no finite zeros. And now what we're doing is we're actually sketching, or in our script file, and let me go ahead and show you what I've done in MATLAB. I went ahead and captured that. Here is the script file, vid 9.4 in MATLAB. And what's happening now as I'm discussing this, as you can see, we first found, and let me go ahead and get back to the MATLAB script. We first issued a couple of commands to define the numerator and denominator. You could have just put in 10 here and a vector, open bracket 1 comma 10, close bracket, and defined H1 that way. We then looked at the poles and the zeros with a couple of other functions. Then figure 1, we went ahead and sketched, or MATLAB plotted, the impulse of that transfer function H1. So if we now come back and look at figure 1, that's now the impulse response, and in fact that's what we would have expected. And here are just some ways of fancying that up. I went and put a title on it. That's the impulse response of a low-pass filter. The horizontal axis is time, and the vertical axis is the response voltage of our low-pass filter. Then we wanted to excite the system with an exponential waveform. These are now just comments with these percent signs, but we now created a time vector. We go 0, colon, and we have time steps of 0.01, and then another colon up to a time interval of 3. We can now produce x1. I should have probably called that x1. This is now x is equal to exp, the exponential function, minus 2 times t, and in figure 2, we've sketched that particular waveform, and in fact, that's what we would expect. We didn't change anything on the amplitude of that. It has an amplitude of 1. Then what we want to do is go ahead and apply that to the low-pass filter through the linear simulation function, LSIM. So we have the transfer function H1, the input, or how we're exciting it with X, and the time vector associated with that, producing an output Y. And you can see that I went ahead and followed that command with a semicolon so it wouldn't spit on the screen all of those data points for Y. In figure 3, we've now plotted that particular output response due to an exponential excitation or input. And this is now what we see. And that's consistent with what we've already expected. Then, just for grins, we went ahead and basically jumped into Unit 10. We said, oh, MATLAB's powerful. Let's just execute the Bode command. And that's in Figure 4. And there's our Bode plot. We have a magnitude Bode plot and we have a phase Bode plot, all with respect to frequency in radians per second. Here's 10 radians per second. And we would expect something to be happening there since our pole was at -10. And in fact, we'll learn how this can be sketched in a straight line approximation. And in fact, I've already copied in some of those figure windows. Here's now our Bode plot. We will learn how to do a straight line approximation. We'll go out to 10 and then we'll come down 20 dBs per decade because it's a single pole system. And that would just keep going and going. That's our magnitude response. We will start with a 0 degree and we'll finish with a -90 degree because we have a single pole, and then we'll connect those with a straight line. That's supposed to be a straight line. And we'll make that go through -45 degrees right at the break frequency or the pole, which was at 10 radians per second. That's our Bode plot, and we'll talk obviously more about that in Unit 10. But this now says that if I excited this signal or this system that has this for a frequency response with a sinusoid of 1 radian per second, I should get out an amplitude that is scaled by 0 dB. And 0 dB is a gain of 1, an absolute gain of 1. And the angle, I won't have too much delay, but I will have a little bit of a delay based on this point right there. It's about 6 degrees of phase shift. However, if I put in a signal that had a frequency of 100, which is out here, then you can see that I'm now 20 dB down, and that now corresponds to a factor of 1/10 in terms of absolute, and the angle that I now have is I have now almost a phase shift of -90 degrees. We are going to actually inject a waveform that has a frequency of 30. So here's 10, here's 20, here's 30. We are going to inject a signal at 30 radians per second, and this is now the gain in dB, so it looks like it's about -10 dB, and this is somewhere between -45 and -90. Let's say it's about -70 something. Let's say -72 degrees. We should expect those changes at the output. So if we now go back, I don't want to go back that way. Let's go back this way. Now what we want to do is shorten up our time horizon so that we now have a time horizon of 1 second, since that will give us plenty of cycles since we have a 5 Hertz waveform. Here's our 5 Hertz input waveform, and I am calling this x sub 2. Then once we have that input waveform created, 2 pi times 5 times the time, t sub 2, we can inject that into our system low-pass filter and find the output through this linear simulation function. And then I'm going to go ahead and plot not only the input, but also the output. The input will be with a black line. That's what this K says. And the output will be in a red curve. And that's now what we want to see in Figure 5. And you can see then that there is a short transient. And after that transient, and now we could say, okay, we're definitely beyond that transient at 0.6. So now what's going to happen, and we want to now find this particular point. So you can, in what I'm doing, is actually finding that particular point, and I don't know if I did it in MATLAB or not. Let me go to MATLAB and see. That may not have, oh, it did. So I did touch it with my pointer, and that now finished up the execution of this script. What I did was I actually went ahead and said, let me obtain a graphical input from the last figure window, which was figure window 5, and then from that point I was able to determine what the magnitude and angle was if I did a good job of identifying that, and then I went ahead and found those values analytically. I evaluated the polynomial of my denominator at the frequency 30 roughly, which is I, which is the square root of -1, so it's J30. Here's 10 times pi, so that's J30. I'm evaluating the denominator and I'm dividing that into 10 so that H1 J30 represents the complex number of my transfer function when I evaluate that transfer function on the imaginary axis at the point J30. Then I can find the absolute magnitude by doing the absolute, and if I wanted to, I could find that in dB, but I can now convert that dB from the Bode plot into this absolute magnitude, and I can also convert the angle into a delay by dividing by 30. Let's now return to where we were, and this is now where we were talking, and we found that the magnitude of our transfer function at 30 was -10. The magnitude of, or the angle of our transfer function at 30 was about -72, and we can now back out the actual values in terms of absolute numbers. The scaling factor, which I'm representing as a capital S, is now 20 log base 10 S. That's equal to -10. If I solve for S, I find that the gain should be dropped down to about 0.316 of where I started, and I started with a gain of 1 in my input signal X sub 2, so I should be down to about 0.3 or 30% of where I started, and that looks to be about true in my figure 5 in the red curve. I'm about 30% of where I started. Finally, the delay I can find by the phase shift. If I convert that delay in degrees into radians, I have a radial shift of -1.26, and this was in the argument of my cosine. I have an omega naught t minus 1.26. Well, I'm actually wanting to factor out the omega naught from that so that I can see what my delay actually is. And that's where this delay now is coming from, of 1.26 divided by 30, or 0.04 seconds. And if I go back to MATLAB, the actual results of executing that script file, here's the transfer function, there's the pole, no zeros, then here's the complex number. I'm sorry, there are the values of when I clicked on this particular location. I was at a frequency, I'm sorry, a time of 0.6. So here's my time of 0.6417, and I would compare that. I clicked at this particular point, and this has now a time value of 0.64 roughly, and the amplitude is 0.297. So here is now the scaling factor, about 0.3, which is what I was expecting. So that's what happened. So this magnitude, if I went over here, this should be about 0.3. And I'm comparing that now with this peak of the input, so the delay between this peak of my input and the peak of my output is the difference between 0.64 and 0.6, or 0.04, which is what I was expecting that delay to actually be. Here's my delay of minus 0.04. The magnitude is about 0.3 when I evaluate the transfer function h1 of j30. Here's the complex. Here is now h1 at j30 as a complex number, and it's in rectangular form. This now would be converted to the magnitude of that. So I now have the absolute of h1 of j30, and I have the angle of h1 of j30, and that is in units of radians. I could then convert that if I wanted to degrees, but that's what I found in the Bode plot was in degrees. But I hope this now is showing you that if you excite or if you shake a linear time invariant system at a given frequency, in this case I'm shaking it at 5 hertz, so I should see 5 peaks of this black curve, 1, 2, 3, 4, 5 in 1 unit of time, and I do. Then I actually obtain, after the transient period, which is going to be roughly 0.5 seconds in this particular case, then after that transient I should see an output waveform that's at the same frequency. And in fact, if you measure the distance between this peak and that peak, you should see that it's the same as the distance from this peak to that peak. And that's what we should be starting to gain some insight into after this particular video. And now what we want to do is figure out how to find that, or actually verify why in fact the sinusoidal steady state output is what it is, and how can we find and use that information to quickly find y sub 2 of t in the sinusoidal steady state.